Good morning, grade 10s. So in today's lesson, we're going to go over the inverse of quadratic functions and radicals. So I know that this lesson is, you already saw the PowerPoint for it yesterday, but I'm just making a video lesson for today. So what we're going to learn about is just how to find the inverse function of a quadratic function, which should, at the very beginning shouldn't look too different. We're still following the same idea as before. The only difference is that we have to consider that the restrictions we're going to have, and also we're going to be looking at radicals and how to perform operations with them. So quick recap, what is an inverse function? We already talked about this. The inverse function basically undoes what the original function with f of x would originally do. And as we already mentioned, the inverse of a function may not necessarily be a function in itself, okay? So you want to be really careful with your notation. If you write f inverse at x, then you're specifying that the inverse itself is a function. But sometimes what we'll do is we'll simply do this if we want to emphasize that it's the inverse, but maybe not a function itself, in which case it would just be a relation, okay? So it would be a relation, but not a function. And we also know that we can graphically find the inverse relation by switching the x and y coordinates of the original function. And then we learn how to solve it algebraically, which is what hopefully everyone knows how to do. You switch the x and y coordinates, you switch your position in the equation, and then you simply solve for y. So we will look at some examples anyways of how to do this, but let's first consider what happens when we find the inverse relation of the parent. Let's start with the easy parent function, the one that we're familiar with. F at x is equal to x squared. So we know that this is the equivalent to writing, sorry, my coffee machine's going off there. This is equivalent to writing y is equal to x squared. So what we do in this case is we simply can exchange our x and y coordinates, and we could write x is equal to y squared, and we could try to isolate for y and then see what happens when we do that. But right before I even get to that, to the algebraic part, the algebraic inverse, let's actually graph out the parabola itself, and let's just look at the graph to figure out what the inverse relation is. And then what we're going to do is consider what the domain and range of x squared and its inverse relation will be. And then the final thing we'll do is we'll determine whether the inverse of f at x equal to x squared, whether it's a function or not. So looking at our table of values here, we know that for our x squared, our parent function here, we should hopefully recognize the key points that we have there. So we have -2 and 4, -1 and 1, 0, 0, 1, 1, 2, 4. So I'll let you just decipher that. I know I didn't go through it in detail, but I think everyone hopefully knows how we got these points right here. All we did was simply just take -2, we squared it, you got 4, -1 squared, you get 1, and so on. And what we notice is that if in an inverse relation, all we do is switch the x and y. So the 4 and -2 will switch, the 1 and -1 will switch, the 0 and 0 will switch, and the 1 and 1 here switch, and then of course we got 4 and 2 there. So notice that in an inverse, the inverse relation is actually basically this is what the graph will start to look like. So we have 0, 0, 1, 1, 4, 2, 1, 1, -1, and 4 and 2. And we notice that it basically is a parabola, but it opens up sideways. And I think we have seen this already. We actually saw this at the very beginning when we were considering inverse relations. So what we notice is that it's actually a combination of two different types of functions. So what it is, and I'll actually erase this so you can see it more clearly. It's almost like we have the one positive square root at the top here, and then we have another negative square root at the bottom. So together it's two separate functions. But notice that they are together itself, not a function. How do we know that? Well, I'm doing the vertical line test right now, and I can tell you it's failing at several points, right? So I can see here that definitely is not going to pass the vertical line test, because we can see that if we take a straight vertical line, it's going to be hitting the function more than once. So it is definitely not a it's definitely not a function. The inverse is not a function itself. So the inverse function is plus or minus the square root of x. How do we get that? So algebraically, and I know we set this up, so I'll just repeat this again. What I did is I exchanged the x and the y. So we have x equal to y squared. And then I know that if I want to isolate for y, I simply take the square root on both sides. And then I end up with y is equal to the square root of x. And remember, I write plus or minus. And then all I have to do now is simply write this as f inverse is equal to the square root of x. So that is our, oops, plus or minus. So that is our inverse relation there. So we notice that it is a relation, but it's definitely not a function. So the domain of the parabolic function, let's look at the first one. The domain of the parabola there is xer, and the range is, as we already saw here, is going to be yer, because in the purple graph, the original parent function, we noticed that the range is limited based on the vertex, right? So it has to be greater than whatever the minimum value is, right? Remember, we discussed that at the very beginning. We talked about how parabolas, the domain is always xer, the range is going to be limited based on what the vertex is, right? So if it's opening up, then it's going to be greater than the minimum. If the minimum value, if it's opening down, it's going to be less than the maximum value, right? So we kind of discussed that already. And then in the inverse relation, we noticed that XCR, it's basically the domain and the range are going to switch, right? So if we go back to our picture here, looking at the green parabola opening sideways, we notice that the domain is not going to be limited. So for the domain, we have to have a restriction that x must be greater than 0. So as long as it's greater than 0, then you could take the square root of it, right? You want to think of it that way. You know that you can't take the square root of a negative number, so it has to be positive. So x would have to be positive in this case. But because we're considering positive and negative square root, you could, at least for the inverse relation, we notice that we could have any number, right? We could have a positive number or a negative number. There's no restriction there. So we notice that the range is actually unlimited there. So just notice that the domain and range just swap, right? And that's a really important concept for you to understand. So the inverse of the f at x is equal to x squared is not a function because it doesn't pass the vertical line test. But what we do notice is that if we make a change to our domain, so that we only allow one part of the inverse relation, then we actually will get a function. So what we're looking at in this case is how can we restrict our domain of the parabola so that when we find the inverse, we actually do end up with a function. That's really what we're trying to do. So we're trying to limit our domain of the original function so that when we find the inverse, we actually end up with a function by definition, right? That passes that vertical line test. So what we notice right away is that, and I hope this diagram kind of helps, and I'll try my best to kind of split it up here. If I look at this this function on this half, the left side of the parabola right here, just gonna give you a little description here. If I look at the left side of the parabola right there, I notice that left side of the parabola is going to be when it's transformed, it's gonna flip over and go to the bottom half, or sometimes we call it the lower branch. Instead of talking about the lower half, we talk about the lower branch of the inverse relation. So this right here will transfer over to this side here. And why this is important is because we realize that if we restrict our domain and we say, hey, you know what, I only want to focus on the parabola on the left side of the vertex, then in my inverse relation, I only focus on the negative square root of the inverse relation. So the left side of the parabola, if I restrict the domain to the left side, to the left of the vertex, then I end up with only the lower branch of the inverse relation, or this would specifically be the negative square root, right? Now, a good question is, what about the other side? Well, if we go to the right side here, if I go to the right of the vertex, so the right hand branch of the parabola right there, I notice that will correspond directly with this upper half of the inverse relation, right? So the parabola, if I restrict my domain to the right of the vertex, I will actually end up with the upper half of the inverse relation. And the upper half of the inverse relation is simply the positive square root of x. So this is a really important idea, because even though the inverse of the whole parabola, and I hope you understand that the whole parabola with no domain restricted, I noticed that is the inverse of that is not going to be a function because it fails the vertical line test. We already saw that. If we restrict our parabola, our original parabola to the left of the vertex or to the right of the vertex, then I will end up with an actual function. So I'm hoping that that is starting to make sense to you guys. So if I take my domain, if I look at the original function, I restrict my domain to the left of the vertex, then I will end up with then I will end up with the lower half of the inverse relation, which is a negative square root. If I restrict it to the right of the vertex, then I end up with the positive square root. And then in both cases, if I restrict my domain of the parabola, I actually end up with a function as an inverse function, not just an inverse relation. So I'm hoping this kind of makes sense. So that's really what I'm trying to say here. So again, what we're noticing is that if we restrict our domain of the original function, then it makes it easier because then we can just get the upper half of the inverse relation or the positive square root. I'll just write that down. Or we can limit it so that we only get the lower half of the inverse relation, which is the negative square root. And if we only get the positive square root, or we only consider the negative square root, then we have a function. Does that make sense? Hopefully it does. So conclusion here, when we look at this, is that the inverse of a quadratic function is not a function itself, but if we focus our attention on whether on just one half of the parabola, so we go to the left of the vertex or to the right of the vertex, then we can end up with an inverse function. So just keep in mind that if the inverse of a quadratic, and we actually kind of already saw that, the inverse of a quadratic is that is parabolic, obviously, opens, if it's opening up, then it's actually, then its inverse relation will be opening to the right. And if it opens down, then the inverse will be opening to the left. And we can actually see this by looking on decimals. So I'm actually going to open up decimals so you can see this. So let's do another example. I actually want to show you with a negative one here. So let's say I switch them around. So to find the inverse, all I do is switch around the x and y coordinates so you can even see what it looks like. I should isolate for y, but you'll notice that you don't have to necessarily do that. So now what I noticed is if I have a parabola that opens down, then I can see here that the inverse in blue will be opening to the left. And this will still be happening even if I switch it around a little bit, right? Even if I decide to transform it. Let me just make it a little more funky there. I just want to show you that we still end up with this relation. Oops. And of course, I'm just going to switch this around, y minus 4 squared. So notice I'm just switching the position of the x and the y. And again, I could isolate for it, but I don't have to do that. So what I noticed is that if my parabola opens down, then its inverse is going to be opening to the left. But if the parabola opens up, then its inverse will be opening to the right. Okay, so hopefully you can see that and it's pretty clear there. However, as I mentioned already, even though the inverse relation of the whole parabola is not a function, if you limit the domain of the original function, then you can definitely create an inverse function. So when you're finding the inverse of a quadratic function, the positive square root function, and again, the positive square root is the one we looked at the very top here. So if we go back to our example here, this is the positive square root that I'm looking at, just this upper half here. So the positive square root, looking at that one right there, that is going to be that is going to represent the upper branch of the sideways parabola, while the negative square root, so the one at the bottom there, the one that went like this, is going to represent the lower branch of the sideways parabola there. So I'm hoping that makes sense so far. And again, the positive square root function, it corresponds to the right-hand side of the parabola, and the lower branch corresponds to the left-hand side of the parabola. I hope that kind of makes sense so far. So what we do is to find the inverse algebraically, and I hope this makes sense. So to find the inverse relation algebraically, what we do is we exchange the x and the y coordinates just like we did before, and then we simply solve for y. So a little caveat here, in standard refractor form, you can't really easily isolate for the independent variable, right? And I actually gave you a test question that was similar to this. if you recall, I think the function was f at x is equal to x squared. I can't remember the whole question, but I think it was something like this, minus 4x minus 5. I think something similar. And I think I asked you to make it equal to 8 and then try to figure out when it would be equal to 8 there. And I actually don't remember this question fully. I think it was plus 5 like that. Maybe it could have been like that. And I think I told you that f inverse is equal to, sorry, I asked you to find f inverse at 8. So what I wanted you to do in that case was simply let f at x equal, there's a bit of a shortcut for that one. You're supposed to let f at x equal, since you're finding the inverse function at 8, what I wanted you to do specifically was kind of work backwards and let, since 8 was the input of the inverse, then it would be the output of the original function, right? So you simply would let f at x equal 8. And then you have to solve this by factoring. But a different way that you could have approached this, I don't know if a lot of you actually ended up doing this, was you could put this in vertex form. And if you have it in vertex form, then you could isolate for x. Because what some of you were trying to do was you were actually trying to figure out what the inverse was. And so to find the inverse, and it was a good attempt, you basically switched the x and the y, and then you ended up with x is equal to, this is actually not what you're supposed to do. So I'm just letting you know this is not what you do, but I just want to show you what some of you were trying. Then you switched the x and the y, and you were trying to isolate for y. The problem with trying to isolate for y here is that y is not you can't really get y by itself. You could try to factor and see if you do that, but that's not going to work when it's equal to x, right? There's no way that I can really isolate for y. You could try it out, but it's not going to work. So what we noticed is that if it's in standard or factored form, you have no other choice but to do something important here. You're going to have to switch this into vertex form. So even if it's factor form, by the way, you would think, you're good with factor form, you still would have to switch it to, and remember, there's no shortcut to go from factor form to vertex form. You'd have to go from factor to standard by expanding and simplifying, and then you'd have to go from standard to vertex. So luckily, we actually know how to go, how to switch to vertex form. We just did that in the last lesson. We completed the square. So what we're going to do in this case is we can simply put a function into vertex form if it's not already in vertex form, and then we can isolate for the independent variable, okay? Sorry, not independent variable. I meant to write dependent variable, okay? Then you can isolate for it. So by rewriting y as f inverse at x, we're simply going to, like I said, restrict our original. Before we even do that, we need to restrict the original domain of the which is a quadratic function itself, right? So we have to restrict it to the left of the vertex or to the right of the vertex. So let's look at an example here. So we are given this function, and then we're asked to find the equation of the inverse relation, and then find the equation of the inverse function itself. So first, let's find the equation of the inverse relation, or actually it's going to be an inverse function, because eventually because we decided to restrict our domain. So you're going to probably look at this and say, well, why is it specifically saying x greater than or equal to -3? I'm going to explain why. So the first thing we're going to do is we're going to complete the square. That's the first thing you need to do. You need to complete the square because, unfortunately, you need to get it in vertex form in order for you to isolate for your independent variable. Isolate, or in our case, independent or in our dependent variable, which would be y. So what we're going to do in this case is we're going to try to, we're going to group them up. So I'm going to skip a couple steps here. We're going to group up the first two terms, right? Then we take our middle term right here, and we take, and again, we found that by simply factoring out the 2 from the first two there. So we take our middle term now, which is 6, we divide it by 2, and then we simply square it. And just a little side note, yesterday's lesson on determining the max or min, I added a few more slides to it, so please go back to it and reread some of the notes. I think it's starting on slide 12. I added a couple more slides, which I hope will help you just clarify a couple of points. I added one more example about finding the maximum or minimum. So please go over that lesson again if you don't mind. So we're going to take 6 divided by 2, which is 3, and then we square it, which gives us 9. So then in our next step, that means that we're going to be adding a 9 and then subtracting a 9. So what we're going to do now is we're going to take our -9 right here and simply move it outside the bracket. But before I do that, I have to recognize that it needs to be multiplied by 2. And again, it's multiplied by 2 because it's inside the brackets, which is itself, the whole entire, all the terms are multiplied by 2 there. So before I move it out, I just make sure I multiply by 2 there. So now I end up with 2 times x squared plus 6x plus 9, and then negative 9 times 2 is going to be negative 18. And then my next step here, and I know I skipped some steps here, I noticed that x squared plus 6x plus 9 is a perfect square trinomial. So I can factor it like a perfect square trinomial. So I just have to think to myself, all right, this is a perfect square, that's a perfect square, and this 6x is the sum of the products of the square roots. So I end up with x plus 3. I simply take the square root of each, or I could do sum and product. And then over here, I'm just going to do this on the side. Negative 9 times 2 is negative 18. And of course, negative 18 plus 14 is negative 4. And that's how I ended up with negative 4, by the way, right there. So now that it's in vertex form, what I'm going to do is simply replace the x and the y. And now notice that f of x is simply the same as y. So I swapped them around. And I'm actually going to add on the transitions. I personally myself really like that. Makes it easier. Okay, so what we're going to do is switch the x and the y. So then we end up with x is equal to 2y plus 3 squared minus 4. And what we're going to do now, and now that we have it in vertex form, we can more easily isolate for the missing variable, which is, sorry, not the missing variable, for the dependent variable, which is what we're trying to isolate for. So keep in mind, I made a little typo before. So we're trying to isolate for y now. So what I'll do is I'm simply going to do my best. It's like solving an equation. The only difference is that there's two variables, which kind of throws people off. But remember, the x, just treat the x as if it were a regular number. So remember, whenever you're solving for a variable, you are simply, the best way to think of it is, I always like to do this. I like to circle that variable we're looking for. And just remember, do everything in your power to get that variable by itself. That's really what you're trying to do. So if I'm trying to get the y by itself, I'm going to first bring the 4 over. And I do that by adding a 4 to both sides. And I'm showing you all the steps here first, and then I'm going to show it to you a little bit more neatly. So we have x plus 4 is equal to 2, and then it's going to be y plus 3 squared. What do I do next? Well, the next step, I always want to get rid, like I said, get rid of what's furthest away from the y first, and then we'll get closer and closer to isolating, getting the dependent variable y by itself. So my next step here is to divide by 2 because I want to get rid of the 2 in front. So I do the opposite of multiplying, I divide. So I divide by 2, and then you end up with x plus 4 over 2. So notice that this is really similar to what we did when we solve for inverse functions in general, right? For linear functions. It's not that different, right? The only difference is that there's a few more steps. Then what we do next is we take the square root. So we don't subtract the 3 yet. We take the square root. So take the square root. And then we end up with y plus 3 is equal to positive or negative square root of x plus 4 over 2. So we are taking the positive and negative square root of x plus 4 over 2. And then my very last step here, I simply subtract the 3 on both sides. And now I end up with the whole entire expression that I want. So we have x plus 4 over 2, the square root of x plus 4 over 2, positive or negative square root. And we are simply going to subtract off the 3, and then we end up with y by itself. And now that y is by itself, remember we have this not write y, we're going to write f inverse, right? So I'm just showing the steps there once again. So you simply isolate for, oops, and I had some repetition here, I don't know where's that. So again, we simply added the 4 to both sides. So I'm just going to extend this out a little bit. I might as well make it bigger now that I have a bit more space. Oops, not. Okay, sorry guys, let me just try to make this bigger. I personally, oh geez, I'm making it smaller as I go along. Okay, I think this should work a little better, hopefully. Sorry, I'm just trying to make it a little bigger there for you. I know sometimes the font ends up being a little small. So we take the positives, we find the positive negative square root of x plus 4 over 2, and that's equal to y plus 3, and then of course we subtracted the 3 on both sides. So keep in mind that I could put the negative 3 in front of the square root, or I could put it right after the square root. We tend to, it doesn't make a big difference, but you'll notice that there's a bit of a benefit sometimes to actually putting the constant in front of the square root. It doesn't make a huge difference, but it sometimes is a bit of a benefit to put it in front of the square root as well. So I'm hoping that makes sense so far, and I'm hoping that was clear as far as we know. Okay, so what I'm going to do is I'm going to go to the next example here. And again, notice that, oh, sorry, and I'm actually not done yet. Notice that now I just simply wrote that as y. I did not actually write f inverse because it's actually, sorry, and I definitely did not write f inverse x because it's actually not a function. So what I have right now is that the inverse of the relation is negative 3 plus or minus the square root of x plus 4 over 2, which is a bit difficult to say, but essentially what that means is if my red, and again in red, here's my parabola. So my parabola is going to be my original parabola. What was it? It was in vertex form. Sorry, I had to go back a little bit. Kind of forget what it was. It was f at x is equal to x plus 2x plus 3 squared minus 4. So x plus 3, 2x plus 3 squared minus 4 means that it has a parabola at negative 3 and negative 4, right? And this is coming from the fact that in vertex form, we can easily identify the vertex, right? So it's going to be 2x plus 3 squared minus 4. So remember, that means that the vertex, and I know I'm reviewing a lot here, the vertex is going to be negative 3 and negative 4. And how do we know it opens up? Well, the a value is positive. So we already know a lot from the vertex form, right? And to find out what the whole function looks like, you might notice that normally in the original parabola, it would have gone from 0, 0 to 1, 1. Now it's going from negative 4, negative 3, and 4, and it's actually going up by 2 instead of just by 1. And same with this, it goes up by 2, sorry, it goes up by 2 instead of going up by 1 on the left. So we can see here that this is our new parabola. And then how do we find the inverse relation? Well, we know that the inverse is just going to be the opposite. Instead of having a vertex at negative 3 and 4, it's going to have, it's not called the vertex, but it's going to be called, I'll call it kind of like the tip of the sideways parabola is going to be, in this case, negative 4 and negative 3. So notice that I simply switched the x and the y. And then the point right here, which would have been, I'm just picking out a couple more points here. This would have been negative 2 and negative 2, obviously stayed the same, but negative 4 and negative 2 switched over to, and I'll do this in a different color so you can see a bit of a difference. Negative 4, negative 4, negative 2 will now switch to negative 2 and negative 4, like that. Right, so we just switched the x and the y coordinates. So that's how I got the sideways parabola there. So what we notice is that if we restrict, obviously our function, the inverse, is not is not a function itself, but if I focus my attention on the function, on the parabola to the right of the vertex, so let's say I only look at the parabola to the right, then I'll notice that this itself will correspond with the upper half of the parabola, upper half of the square root function, right? Which is a positive square root right here, and this itself is actually a function. And if I decide to focus on the left side of the parabola, then I will get the negative square root as the inverse relation, and that is itself a function, right? So if I focus my attention on to the right of the parabola or to the left of the parabola, then I will end up with just one side of the inverse relation, which itself will be a parabola. So in our case, that's why we restricted it to the left, to the right of negative 3, because that would ensure that my inverse is actually just the upper branch of the upper branch of the sideways parabola, which itself would be a function. So that means that f inverse is going to be simply negative 3 plus the square root of x plus 4 over 2. So if I just focus on the positive square root, sorry, if I just focus on to the right of the parabola, then I know that that means its inverse will simply be the positive square root there. And if I had focused on the left, I didn't actually do this, but let's say I had focused on the left of the parabola, the only difference is that the inverse function would be negative square root of 3 minus the square root of x plus 4 over 2. So the only difference is that I subtract the square root. So keep in mind, this is the really important part, and this might be a really good test question, by the way, a little hint there, is I might try to throw you off by changing the sign of that constant right there. But that's not actually what's making the difference of whether it's a function or not. It's about whether the square root itself is positive or not, right? So remember, if I decide to look to the left of the vertex, then I'm going to be looking at the negative square root. So I have to subtract off whatever is in the square root. But if I look to the right of the parabola, which is what we did in this example, then I'm going to be adding what's in the square root, right? Or I'm going to be considering the positive square root value. So again, you cannot use, I know when we take the square root, we have to consider positive and negative value. You should always do that. But remember, in order for it to be an inverse function, we need to make sure that we only consider the positive square root or the negative square root value. Okay, so I hope that kind of makes sense. So either the upper half of the sideways parabola or the lower half of the sideways parabola. So I'm hoping that kind of makes sense. I know there's a lot of new, like I said, a couple new concepts there, but some of it was a little bit of repetition. So hopefully it was slightly easier to make sense of it now that you learned about what inverse functions are. Okay, our next part is looking at working with radicals. There's not going to be tons of questions on the test about this, but there will be a few, so you want to make sure you know this. So a radical is a square, a cube, or any higher order root. So if I'm taking the square root, a cube root, an nth root, and we're going to look more at radicals later on. So we're not done with radicals. We're actually going to revisit radicals in the next unit. But I want us to start just looking at the algebraic side of it, just how to kind of manipulate them. We will go back to radicals later on, though, for sure. So we're definitely not done. So as an example, the square root, and again, if you don't actually write a 2 outside, like if I don't write anything there, it's assumed that I'm taking the square root. You always assume it's the square root there. The square root of 4 is obviously 2, and how do I know it's 2? Because I know that 2 squared gives me 4. The cube root of 27 is 3 because I know that 3 cubed gives me 27. The fourth root of 625 is 5 because I know that 5 to the power of 4 is 625. So I'm hoping this all makes sense. I'm simply just taking the root of each of these different numbers. We're just trying to figure out the root is working backwards. So you're trying to figure out what number is multiplied by itself that many times, whatever the root is, to give me the value that I'm taking the radical of, right? So those are all different radicals. So radicals don't have to be perfect squares. I think we're used to always having perfect squares because we talk about perfect square factoring or difference of squares, but it doesn't have to be a perfect square. And that's what you'll notice a lot is that a lot of the examples that we do now, the square root is actually not going to be the square root, the cube root, whatever root you're looking at is actually not going to be a whole number. So the radicals themselves don't have to be perfect squares or perfect cubes, right? So what we're doing now is we're going to be performing operations on radicals, and these new radicals are actually going to we're basically going to have an entire radical. So that means that the coefficient is going to be 1 in that case, or we're going to have a mixed radical where the coefficient is not 1. So what I mean by that is something like this. So we're going to have square root of 20, which obviously square root of 20 is just going to be a radical because there's no number in front, right? Again, you almost want to imagine that there's a 1 in front, whereas the mixed radical is going to have a whole number multiplied by a radical itself. So you can have a whole number multiplied by a radical as well. So I'm hoping that makes sense as well. And again, this is more of a definition. And sometimes what we're going to notice is that we want exact answers, and we want to be able to reduce our radical answer. So we could grab a calculator and find the exact answer, but sometimes we actually want to give the answer more precisely. So what we want to do is we want to be able to write our answer as a mixed radical, which means we will have a whole number and a square root next to each other. and they're going to be multiplied, right? So it's just assumed, kind of like this is basically like a variable. You almost want to think of it that way. It's very similar to that. If I write 3x, it's assumed that you're taking 3 times x. Well, it's the same thing. 3 square root of 20 is assumed that you're taking 3 times the square root of 20, right? But we just want to write it, leave it as a radical a lot of times, right? So that we get a more precise answer. So let's see what happens when we simplify something like square root of 3 times square root of 8, so to lowest terms. Well, to multiply radicals, it's actually not too difficult to do this. What we simply do is we write both numbers under the same radical and we multiply. So a good rule here, the product of a radical is the radical of a product, which sounds really confusing, but it's basically just saying if you're multiplying two radicals, you can simply multiply the numbers under the roots, and then take the root of that product, right? That's all it's saying there. So in our case, the square root of 3 times the square root of 8, we can rewrite that as the square root of 3, times 8. So we simply multiply the two numbers there, and then we take the root of that. We notice that this ends up giving us the root of 24. And what we want to do now is we want to see if there's a way that we can write this in simpler terms. So what you might notice is that 24 itself, we can leave it as 24, but if we want to write this as a mixed radical, we might notice that 24 itself can be broken down into this. We know that 24 is the same as 4 times 6, right? So we know that 4 and 6 are its factors, another two factors. So if I rewrite this as 4 times 6, the reason this might be helpful to us is because we end up with the square root of 4 times 6, and 4, notice that 4 is actually a perfect square. So what we're going to do is we're going to rewrite it as the square root of 4 times 6, and then that square root of 4 times 6 is going to be broken down a little bit more. And we're going to break it down so that one of the radicals contains a perfect square. So we break it down into square root of 4 times square root of 6, and notice that square root of 4 itself is a perfect square. What does that mean? That means that you can find the square root of it. Sorry, the square root of that answer is a whole number. So the square root of 4 is simply going to be 2. And of course, the square root of 6, that is not a nice friendly number. So we leave it as it is. And what we notice is that we end up with a mixed radical, which is a little bit simpler to work with than the square root of 24. And that's basically what we're doing in this case. We're always trying to figure out, is there an easier mixed radical that I can replace my current radical with, right? Is there an easier mixed radical that I have there? And again, what we notice here is that the mixed radical, when you're trying to find the mixed radical, you purposely want to rewrite the number in the radical as the product of one perfect square by another non-perfect square. And if it's another perfect square, that's even better, right? But then that means that you can take the square root of the whole number. But generally speaking, we're focusing on radicals of non-perfect squares. So what you want to do is break it down into a product of one perfect square and then another non-perfect square. That's really what you're doing. So the good thing is, not only can we simplify radicals, but we can actually do different operations with them, right? So we can add, subtract, multiply, and divide radicals. And it's actually quite easy to do. You basically follow the same rules as before. So our strategy in simplifying entire radicals is to express the number under the radical, like I said already, as a product of two numbers, one of which is a perfect square. I already mentioned that, which results in a whole number, right? So one of them will have to be a perfect square. The other one does not have to be. And then what you're going to do is simply, we simplify the entire radical into mixed radical, and that's our goal right there. So let's say that we have a and b that are both greater than or equal to 0, which means you can take the root of them. If I have the square root of a times the square root of b, I know I can actually rewrite that as the square root of a times b. That's already what we talked about. The product of two radicals is the square root of the radical. And if we are trying to simplify two mixed radicals, and let's say that we are multiplying the mixed radicals like this, well, the general rule is that if there's a mixed radical there and it has these coefficients, I'll call the first one c. So c is a coefficient of the square root of 8, and d is a coefficient of b right there. Then we know that we can multiply this relatively easy by simply multiplying the numbers together and then multiplying the radicals together. And I'm hoping that this looks, I mean, this might look complicated, but I'll give you an easier example. And I'm sure everyone is familiar with this. If I give you something like this, I say 2x times 4x. In grade 9, you learned that you can simplify this by multiplying the two numbers together. So we just focus on the numbers. So we take 2 times 4. And then what did you do next? Then you took the x's and you simply multiplied them together. So we took x and multiplied by x, and that ends up giving us x times x, which is x squared. And so on my next line, I'm going to write, oops. Sorry, I did not mean to do that. I don't know what's going on here. So we end up with 8, and then we have x times x, which is x squared. So 8x squared ends up being the simplified expression there. So we're multiplying the 2 times 4, and then we multiply x times x, which gives us x squared. So what we notice is that this is essentially the exact same. The only difference is that instead of an x, we have a radical, right? So the idea here is that we multiply the two numbers together, c and d, and then we multiply the square root of a times the square root of b. And obviously the square root of a times the square root of b ends up giving us the square root of a times b, right? But the whole numbers in front, which is part of the mixed radical there, we simply multiply the c and d together, right? They're just whole numbers, and so we just multiply the whole numbers together. So again, just remember this concept that we talked about. In a mixed radical, we basically are multiplying just the whole numbers together, and then we multiply the radicals together. Sorry, radicals separately. And then to add or subtract radicals, that's actually quite easy as well, although I think it throws people off initially. We actually add them or subtract them just like we would like terms. The whole idea here is that you can only add or subtract them if they are like radicals. So if it's the same number under the root, if they're different numbers under the roots, then you can't add them. And we'll look at an example of that. So let's look at the first example. So express the square root of 72 as a mixed radical in Low's terms. So what we look for here is we're trying to figure out what two numbers multiplied to give me 72 and where one of them is a perfect square. So what you want to do on purpose is you want to pick you want to try to find the largest perfect square. And the reason you want to try to find the largest perfect square is so that this reduces even more. So for squared, it's the square root of 72. 72 is a hard one because there's actually lots of factors for 72, right? Lots of numbers that could work. So we could try, and so I'm going to even write them out so you can see. So we could have the square root of 1 times 72. We have 2 times 36, so we could have the square root of 2 times 36. We have 3 and 3 works as well. For 3, sorry, just doing a little bit of mental math here. So it's 3 times 34. Nope, that's not even correct. Sorry, guys. Just having a slow day here. It's going to be 24, not 34. So it's going to be the square root of 3 times 24 that we can rewrite this as. So I'm just going to put the square root of 72 right here. And we can continue on with this. So 4, so what do I multiply 4 by to get to 72? So that would be 18. So we know that we could rewrite this as 4 times the square root of 18. 5 doesn't work. 6 does work. So 6 times what gives you 72? That would be 12. So we could write this as the square root of 6 times 12. What else do we have here? 7 doesn't work. 8 works. And we know that 8 times 9 gives us 72. So we end up writing it as the square root of 8 times 9. So these are all the different ways that I could rewrite the square root of 72. I hope you understand that, right? All I'm doing is I'm simply rewriting it as I'm rewriting 72 as the product of two of its factors, right? So all I'm really doing there is decomposition. If you think about, you actually might have done this in grade 9. If you remember, sorry, grade 8, grade 9, when you did the factor rainbow, do you remember writing down all the factors and then joining up the factor pairs? That's really what we're looking at, is factor pairs of 72. So of all these options, I want to pick the one that has the largest radical. So I could have picked square root of 4 times 8 times square root of 8, sorry, square root of 4 times 18, or I could have chosen square root of 6 times 12. But I purposely square root of 8 times 9, because these are perfect squares. But notice that this would be our better option because the 36 is the largest perfect square in this case. So we want to pick 36 and 2 as the factor of 72. So that means that we're going to rewrite 72, the square root of 72 as the square root of 36 times the square root of 2. Okay, so notice that I also could have written it like this, square root of 36 times 2. But in the end, you'll notice that you can actually break it down to square root of 36 times square root of 2. And then this ends up giving me, and oh, sorry, I'll erase this part. The square root of 36 is obviously going to be 6. And so I'm just going to rewrite the square root of 36 as 6. And the square root of 2, I leave it as is because I can't simplify more. Let's look at another example here. So I have simplifying negative square root of 3 times 8 square root of 13. So once again, same rules that we talked about. The whole numbers, the coefficients of the radicals, I simply multiply them together, just like terms. So if I had something like 2x times 5x, you would just multiply them the whole numbers together, right? Not necessarily whole numbers, just the coefficients first, and then you multiply the variables next, right? Together. In our case, same idea. We're going to multiply the whole numbers, the coefficients first. So negative 4 times square root of 8 ends up giving us negative 4 times 8. And then, of course, the radicals, we write them next to each other. So let's figure out what negative 4 times 8 is. That's negative 32. And then, of course, then we have the square root of 3 times the square root of 13. So what we want to try to do is break down that square root of 39. Because 3 times 13 is 39, by the way. That's how I got that. So we want to try to see if we can break that down in any other way. And in this case, we can actually think about it, but 39 does not actually have a perfect square factor. 39 doesn't have a lot of factors, actually. I'm just actually trying to think of anything else that could work. So we have obviously 1 and 39. That's not going to work. 3 and 13. I think that's pretty much it. I don't think there's anything else that would work. So in this case, because 39 is not a perfect square, then that's as far as we can actually go. On the test, though, to be quite honest, I'm not going to give you I'm going to give you examples where the radical can go at least one more time. It can simplify even further. I'm going to try to avoid, giving you an example of a radical like this where it just stops, because I don't want to throw you off too much. I'll try to give you something that will reduce a bit more. It's also more fun if it reduces more, right? You can actually do more. You can go carry out more steps. So let's look at a word problem here. So if you're told that the lengths of a quadrilateral are square root of 12, square root of 18, square root of 27, and square root of 50, find the total perimeter. So what we're going to do is we're simply going to add up all the side lengths here. So we take square root of 12 plus square root of 18 plus square root of 27 plus square root of 50, right? Pretty easy to find perimeter. What we do is add the sides. So if you want to add them, you're going to notice that you can't actually add them unless they are like radicals, right? So the only time that you can add them is if they have the exact, if you can switch them into mixed radicals and then they end up having they have the same number under the root. So only if they're like radicals, right? Understand that. So we go back to a like radical, right? We talked about that. So it's when they have the same number under the root. So what we want to try to do is decompose these radicals and try to see if they have any of them have the same number under the root. And if they have the same number under the root, then we can add them. And again, you want to find the largest perfect square factor of each number under the radical, and you want to factor it out. So what we're going to do first is we notice that the square root of 12, the numbers that it can be broken down into are 4 and 3. So remember, 6 and 2 also works, right? I could break this down into 6 times 2, but again, that doesn't really work because 6 is not a perfect square, neither is 2. But 4 and 3 does work nicely. Square root of 18. Square root of 18, I know I can break down into square root of 9 times 12. Again, I could have used 6 and 3, but that doesn't really work because neither 6 nor 3 are perfect squares. Square root of 27, I hope everyone can see that also can be written as the square root of perfect square times a non-perfect square. It's going to be square root of, it's going to be square root of 9 times 3. And again, we notice that we are already we're going to end up with the same radical. We start to notice a resemblance there. And then, of course, our last one here, we end up with square root of 50, which I can break down the square root of 50 as the square root of 25 times 2. And again, I could have actually done, I could have used a different combination, but I want to try to figure out something that would allow me to actually get a perfect square. sorry, where one of them is a perfect square. So I could have done the square root of 5 times 10, but unfortunately, neither 5 nor 10 are perfect squares, so that wouldn't work. So this is what all these will simplify to. And I know I'm going a little bit fast here. I hope you actually take the time to actually think about why these were given to me or how I came up with these here. Now we're talking about how to actually simplify this and add them. So what we notice is that obviously in every single one of these, there is a perfect square within the radical. And we did this on purpose, right? We wanted at least one of the factors to be a perfect square. So in our case, we have square root of 4, sorry, square root of 4 will be a perfect, that's obviously going to be a whole number. Square root of 9 is a whole number, square root of 9 is a whole number, and square root of 25 is a whole number. So what I'm going to do is I'm going to break apart my radicals, and I'm going to break them apart like this. Square root of 4 times square root of 3, right? I just take the square root of the two numbers underneath the radical. Then I have square root of 9 times square root of 2. Then I have square root of 9 times square root of 3. And then I finally have square root of 25 times square root of 2. So what I'm going to do next is I'm simply going to take the square root of all the perfect squares that I have there. Only the ones that are perfect squares. Square root of 3, square root of 2 are not perfect squares. So I leave them, sorry, that's not going to give me a whole number. So I leave them as they are. I'm just going to take the square root of the numbers that I can actually find the square root of perfectly, right? Again, with all these questions, we assume you're not using a calculator for it, right? You could find out what the square root of 3 is, but there's no point in doing that. We just leave it as it is. But we know how to find the square root of 4 and the square root of 9 and the square root of 25 perfectly. No calculator needed, right? All we end up getting is 2 times square root of 3, which we can write as 2 square root of 3. The square root of 9, which is 3 times square root of 2, which we write as 3 square root of 2. Then we have square root of 9 times square root of 3, which we write as 3 square root of 3. And the square root of 25 times square root of 2, which we write as 5 square root of 2. So in my last step here, and I'm hoping this kind of helps you out a little bit, I color coded this. And I did this because I noticed that this, again, is a perfect, sorry, these two right here are actually like terms. And 3 square root of 2 and 5 square root of 2 are also like terms. So this is really, 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 really similar to what you saw with like terms in algebra. So I'm going to give you an easy example. If the question has said 3x plus 5x, how do you simplify that? Well, we know that we can add the coefficients of like terms. So we take 3 plus 5, which is 8, and then we write an x right next to it. Because we're basically saying if there's 3 x's and 5 x's, then we have a total of 8 x's. That's really what we're doing here. We're saying if we have 3 square root of 2's and then we have 5 square root of 2's, how many square root of 2's do you have? You have 8 square root of 2's. Does that make sense? So all we're doing is simply adding the coefficients of the like terms, of the like radicals. And we do the exact same thing with 2 square root of 3 and 3 square root of 3. We simply add the coefficients in front, right? So that ends up giving us 5 square root of 3 plus 8 square root of 2. And that's all we had to do there. So that's how we add up our like terms there. Sorry, I keep saying like terms because of how similar they're, like radicals, right? And the last example here, what we're doing is expanding out this expression and then simplifying it. This is a little bit tougher, but again, I'm hoping that you always think back to what you already know in algebra. It's actually not going to be too different. What we want to do is simply use FOIL to expand this out. So we're going to take the square root of 3 square root of 3, and we're going to multiply by square root of 3. And then we're going to take 3 square root of 3 and multiply by 2 square root of 2 square root of 2. And then going to our next step, we're going to use FOIL again to multiply the inner term by this inner term. So it's 4 square root of 2 times square root of 3, and then 4 square root of 2 times negative 2 square root of 2. So my next step, I'm going to, like I said, I'm just using FOIL here. So what I'm doing here is I'm simply taking 3, and I'll actually show the steps. I'll go slow here. This example is a little tougher. So I have 3 square root of 3. So in the first step here, times the square root of 3, like that. And then I have my next one, 3 square root of 3. And it's going to be minus. And again, the reason I'm subtracting is because I have a positive times a negative. I have 3 square root of 3 multiplied by 2 square root of 2. And then in orange, my next step is going to be 4 square root of 2 times square root of 3. So I take 4 square root of 2 times square root of 3. And then finally, I have a positive times a negative. That's going to give me a negative. So it's going to be 4 square root of 2 times 2 square root of 2. Okay, so what I'm going to do is I'm going to add this up. I'm going to simplify first and then add them up. So I have 3 times square root of 3 times square root of 3. So square root of 3 times square root of 3, I can actually rewrite that as, and again, going back to what you hopefully remember from algebra, instead of writing square root of 3 times square root of 3, I can simplify that a little more. I can actually write that as square root of 3 squared, like that. The next one I have add 3 times a 2, so I multiply the coefficients, and it's going to give me negative 6. And then I multiply the radicals, and I can't really simplify the radicals, that's okay. I'm going to write that as square root of 3 square root of 2. The next part, I have 4 square root of 2 times square root of 3. There's not really much I can simplify so far, so I leave it as is. I can even leave it like that. And the last one, negative 4 times 2, I multiply the coefficients together. So negative 4 times 2 is going to be negative 8, and then I have negative 2 squared, right? So I have a radical squared in this case. So what happens when I square a radical? So if I take the square root of 3 and then I square it, I don't know why I wrote 3 there, by the way. Sorry, my bad. If I take the square root of 3 and then I square it, you can even grab a calculator and do this. Square root of 3 and then square, you actually end up getting just the number itself, right? Because we know that taking the square root is the inverse operation of a square, right? So now we end up with this expression here, which I'm going to erase because I already wrote it, which can be simplified a little bit more. Absolutely. The square root of 3 squared actually becomes 3, right? As I mentioned already, you end up with just the number itself because it cancels out. The operations cancel out. And then we have 3 times 6, which is 3 times 2, which is 6. 4 times 2, which is 8. And then we end up with, so instead of having a lot of radicals, we actually have only 2 now. And notice that's 2, the square root of 2 squared also reduced to just 2. So what we notice is that we have 3 times 3, which is now obviously 9. That simplified a lot. Square root of 2, so 6 times square root of 3 times 2, which we just leave as square root of 3 times 2. Then we have 4 square root of 2 times 3, and then 4 times 2, which is 16. So let's simplify as much as we can. 4 times 3 is obviously 9. 8 times 12 is 16. And so now we end up with just 9 minus 6 times the square root of 6 plus 4 times plus the square times the square root of 6 minus 16. So notice now that we have 2 like terms, and I did this for you here. I color-coded it. These two have like radicals, right? We have the exact same radical. They're both mixed radicals, but they have the same number under the radical that's left over. So that means that I can simply add the 2 radicals. And again, think about it this way. It's probably easier when you say it out loud. If I have negative 6 square roots of 6 and I add 4 square roots of 6, what do? All I have to do is simply add up my square roots of 6. And if you're ever confused by this, just think back to variables, right? 5x plus 2x plus 5x, what do you have to do? I simply just add the coefficients in front. I get 7x. What's the same thing here? I just add the coefficients in front. So I add negative 6 plus 4, and negative 6 plus 4 is obviously negative 2. So I end up with negative 7 minus 2 square root of 6. By the way, I skipped a step here. How did I get negative 7? This is actually pretty easy. I just didn't show it. I simply take 9 and I subtract 6. So 9 minus 16. Sorry, 9 minus 16 ends up giving me negative 7. That's how I got negative 7. And then I subtract off the 2 times the square root of 6. So it's normally protocol that we put the whole number, like if you have a mixed radical and then you have a whole number, you don't really want to put the whole number first. But again, those are things that I wouldn't necessarily dock off marks, but make sure that you have the correct sign in front. That's really important. And again, we put a negative because obviously it's negative there, and we subtract off the mixed radical because obviously in our case the mixed radical was negative. Negative 6 plus 4 is obviously negative 2. And that was it. So I hope this made sense. And again, there's the homework questions, and hopefully it's a bit more clear now that we did the video lesson there. All right, see ya.